Hello, everyone. Today, I will be talking about our paper, Multi-Predict, Few-Shot Predictors for Efficient Neural Architecture Search. So neural architecture search is the task of finding a good neural network in a given design space for a given task. So as you can see, we have a neural network architecture sampler, an architecture evaluation method, which generates a score, which serves as feedback for the architectural sampler. So recent research such as PRP, NAS, and HELP has shown that neural network-based accuracy predictors can serve as efficient and effective architecture evaluation methods. So there is a significant diversity in neural network architectures and the hardware platforms that they are deployed on. And accounting for these hardware-specific constraints is extremely important in enabling efficient deployment of AI. So as you can see, you have a lot of different architectures and tasks, as well as hardware platforms, which leads to a combinatorial explosion in the architecture platform design space. So let's look at a more concrete example. So let's say that I train a latency prediction model for the task of classification on the FPGA, right? And I train another latency prediction model for the task of segmentation on a CPU. So then the question becomes, can we use the same prediction model for multiple tasks or multiple hardware? So to answer that, let's look at how conventionally the prediction-based NAS works. So if you look at a conventional predictor, we have predictor 1 for NAS bench 101, and the input to predictor 1 is an adjacency matrix and the list of operations. For NAS bench 201, we have another predictor, which takes only the list of operations. And for trans-NAS bench 101, we may have another input encoding entirely. So as you can tell, different neural network architecture design spaces each have unique input encodings, and we refer to these different encodings as WEC. Similarly, different hardware platforms will also have unique properties and descriptors. So these diverse descriptors and encodings pose a major challenge in transferring knowledge between neural network and hardware domains. So in our paper, Multi-Predict, we investigate approaches to encode neural network and hardware that enable few-shot accuracy and latency prediction. As you can see on in the figure on the right, we have the same encoding across different search spaces, which actually enables a multitask predictor. So for multitask accuracy prediction, we encode neural networks with search space independent vectors of metrics based on zero-cost proxies or hardware latency measurements. And for multi-hardware latency prediction, we investigate 3 platform-agnostic methods of encoding hardware platforms. So let's look at the methods of encoding neural networks. So the first one we investigate is zero-cost proxies. So zero-cost proxy is simply a function which produces a scalar value which indicates the quality of a neural network without having to train it. So to generate the ZCP encoding, what we do is we take a set of ZCPs, and for any given architecture, we evaluate those ZCPs on the architecture, and then through those evaluations, generate a vector, which is what we call the ZCP encoding. For hardware latency is simply the measurement of latency of a neural network on a given hardware device. So to generate the HWL encoding, we have a bunch of hardware platforms, and we evaluate the latency of a given neural network architecture in each of those platforms and concatenate that to create the HWL encoding. So these encodings are search space agnostic, and therefore they can be fed to an accuracy prediction model. And this is better depicted by the figure here. So as we discussed earlier, the WEC encoding requires separate predictors for each search space. Right. But as you can see on the right, ZCP and HWL encodings can make these predictors search space agnostic. Further, we also find that ZCP and HWL encodings can enable few-shot accuracy prediction from scratch. So now let's look at the task of latency prediction. So for a single neural network task, we train our latency MLP predictor on a set of training hardware devices. Once the MLP latency predictor has been trained, we can transfer it to unseen hardware platforms through our learnable hardware embedding generator. So before we discuss the learnable hardware embedding generator, we should discuss the 3 platform agnostic methods we investigate of embedding hardware. So the first one is sample embedding. So for a given hardware, how you get the sample embedding is you take a set of fixed neural network architectures, let's say 10 different neural network architectures, and you measure the latency of each of these neural network architectures on your desired hardware. And you can concatenate that latency into a vector, and that is how you get the sample hardware embedding. For the index embedding, what you do is you simply index all of your hardware devices and you convert that to a one-hot representation, and that serves as your index hardware embedding. Finally, the learnable hardware embedding that we discuss in this paper is a learnable embedding table where each row represents a specific hardware device. So for our evaluation, we look at a large set of NAS spaces as well as hardware platforms. For the NAS spaces, we look at NAS bench 101, 201, 301, trans-NAS bench macro and micro. And for the hardware platforms, we look at GPUs, CPUs, mobiles, and other FPGAs and ASICs. So let's begin with the transfer of latency predictors. So we find that transfer learning with the embedding table, the learnable embedding table, and the zero-cost proxy representation can significantly improve the Spearman rank correlation on NAS bench 201 for latency prediction. Further, it is interesting to note that metrics such as ZCP and HWL include domain-specific knowledge about the neural network, and this further increases the sample efficiency of prediction. So now let's look at few-shot latency prediction from scratch, because as we already discussed, ZCP and HWL contain some domain knowledge. So we find that training from scratch with these HWL and ZCP encodings can help the predictor perform at par with help in under 80 total measurements, which is 100 times improvement in sample efficiency. Finally, we also look at transfer of accuracy predictors. So what we do for that is we train a predictor on a neural network architecture search space A, and then we transfer it to another search space B using the ZCP encoding with only 20 samples. And we compare this with using the vector encoding and training the network from scratch. So for this test, we considered 28 NAS search spaces. And in this diagram, the off-white blocks represent an improvement in prediction by using ZCP. Interestingly, we see an improvement in prediction on over 75% of the 784 transfer train transfer pairs. Further, we also evaluate our encodings on neural architecture search. And for that, we employed an iterative sampling strategy akin to BRP-NAS for NAS accuracy prediction evaluation. We find that ZCP encoding significantly outperforms web, and we're able to find near optimal neural networks with just 40 samples as compared to 100 samples if you're using the vector representation. So in conclusion, we introduced multi-predict, a search space, task, and device agnostic predictor for NAS, which enhances sample efficiency. Our proposed NN encoding ZCP and HWL can enable few-shot knowledge transfer across search spaces. In this paper, we also doubled the multi-device latency prediction efficiency by utilizing learnable hardware encodings and a transfer learning strategy. And finally, we demonstrated few-shot transfer of accuracy predictors across 95 domain pairs and enable latency and accuracy prediction in as few as 10 samples using novel neural network encodings, ZCP and HWL. Thank you. You can find the code on the QR on the left, as well as the QR for the paper. And yeah, thanks.